Recall the following work, which is contained in the papers of the following picture, which is contained in the papers of Hassett, Yon, and Lee. And so here's what it says. So first of all, we make a definition, and we denote by mg of alpha. That will be the log canonical model of mg bar with respect to the divisor canonical class plus alpha times the boundary. So for any alpha less than 1, from BCHM we know that there is this moduli space over complex numbers at least, and so that's the definition. And so then the following happens. For any alpha which is between 1 and 9 over 11, we just get mg bar. And then there is a divisorial contraction. There is a divisorial contraction to the space mg when
G is arbitrary, right?
G is at least 3. So, but arbitrary. So with the boundary, that's the statement, that the divisor k plus the boundary is ample. So for alpha equals 1, you obviously get mg bar. And then obviously if alpha is slightly less, then this divisor is still ample. So for some interval around 1, you get mg bar. And so then the interesting question is what happens when you decrease alpha. So I'm telling you the answer contained in those works. So at 9/11 something happens, and there is a divisorial contraction. And then between 9/11 and 7 over 10, it stays constant, this space. And then after that, there is a flip. So there is a flipping contraction to the space which is mg bar of 7 over 10. And then after this flip, you get the space for alpha, which is between 7 over 10 and, let me see, 17 over 28. So this is the beginning of this picture. And then conjecturally, there are some numbers, other numbers, which continue the sequence. And I think the first talk in the afternoon, I think we'll discuss some of these numbers. Anyhow, so there is this picture. And it gets better. So these spaces, they were defined as log canonical models, but it turns out that they have also modular interpretation. And for mg bar, we all know this modular interpretation. So this is the moduli of stable curves, which are nodal. And this turns out to be the moduli of cuspidal curves without elliptic bridges. And this transition from this space to that space goes like this. So if you have some curve and you have an elliptic tails, I'm sorry. You have an elliptic tail, so an elliptic curve intersecting the rest at one point, then it gets contracted to a cusp. And then this space can be interpreted as the moduli space of curves with cusps and tack nodes. And the transition from this space to that space is that when you have an elliptic bridge, so an elliptic curve connecting two curves, so those curves disappear under this flipping contraction, and on the other hand you have these tack nodes. And so stack nodes, you have many ways of gluing them. So that's not an isomorphism. That's a construction. Okay. So that's a very nice picture. And so the question that I would like to ask is this: is there a similar and maybe even parallel picture for the compactifications of AG? And so let me remind that AG is the moduli space of principally polarized abelian varieties. So principally polarized abelian varieties. So after MG bar, this is the next classical moduli space. And they are even closely related because there is the Torelli map, which sends a curve to its Jacobian, which is a principally polarized abelian variety. So we can ask the same question about AG bar. And so what the beginning part for this story is the following two facts. One is that there is one particular compactification of AG which is geometric, which is very analogous to MG bar. Now, let me note here that there are infinitely many compactifications of AG, and there is AG bar star, and this is Bailey-Borel. It also goes by the name Satake and also by the name minimal. And then there are infinitely many toroidal compactifications. And tau here is a certain fan. And fan is a combinatorial object. There are infinitely many choices for that fan, so there are infinitely many toroidal compactifications. And there is this map. So they all map to that minimal compactification. So among these infinitely many toroidal compactifications, there is one compactification for one special fan, one distinguished fan, which is called the second Voronoi fan. So second Voronoi, and this is the normalization of the main component, main irreducible component of APG bar. This is the moduli of stable pairs x theta. So for a non-singular, for an abelian variety, the pair is a principally polarized abelian variety and a theta divisor. And so this extends to the boundary, and there is this moduli space of stable pairs. It's a geometric compactification, and so that's this one special toroidal compactification appears. And on the other hand, so this is, I proved that, and Shepard-Baron proved that another toroidal compactification for the first Voronoi, that's a different fan. This is the log, not log, just canonical model of any compactification. So take any smooth compactification of AG. There is a unique canonical model, and it's this one. So for the fan, which is called the first Voronoi. And this is for G starting with 12. All right, so the question is, is there a picture like this, somehow similar, for toroidal compactifications? And so I have to say how I came to think about this question. It's a very natural question, first of all. Of course, it's easy to come up with this, but earlier this year I gave a talk at Columbia University, and the audience here, so far at least, has been amazingly, quiet and polite. But the audience at Columbia, there are hecklers in the room who heckle the speaker. And so when I was speaking on some other moduli problem, but I mentioned this fact, that there is a unique canonical modular compactification of AG. And so when I said that, Johan de Jong loudly complained that this is not a mathematical statement. That, maybe other compactifications also have moduli interpretation. It's not known currently, but maybe there is one. And so my first reaction was to push back and, told him that you're wrong. And but then I thought, this is something to investigate definitely. So here are some of my thoughts about this. So first, this is already somehow very, very reminiscent of the picture here. There is a definite analogy. There is one unfortunate caveat, that this only holds for G starting with 12. But that's easy to fix, and so let me put it here. There is the following fact, that if you look in the sense of stacks, so the stack for the first Voronoi compactification is the canonical model the relative canonical model over the Satake compactification. And this holds for any G. And so when all of these toroidal compactifications map to the Satake, so it makes sense to talk about the relative canonical model for any G. It's a birational morphism. And so this is the canonical model. And this is a very easy fact. So once I define this compactification, then maybe I'll spend a couple of minutes and prove this, because the argument is very easy and nice. All right. So we can talk about these canonical models for any G. Let me note that the same applies in this situation as well. So there is a similar difficulty here, that for G large, starting with 23 or 24, mg bar is of general type, so one can go all the way up to alpha equals 0. But for low G, these spaces have Kodaira dimension minus infinity, so you cannot go very far. But there is all of these compactifications map to mg bar Satake, to the Satake compactification, where the Satake compactification is simply the closure of this image in the Satake compactification of AG. So that's this is called the Satake compactification of MG. So one can also, it makes sense to talk about all of these moduli spaces about relative canonical models. Then you can do it in every G, starting with 1. Okay, so that's one thing. Secondly, there is another analogy between these two cases. Namely, if we go ahead and make this definition, and call AG bar of beta to be the log canonical model of AG bar together with the boundary, so k plus beta times the boundary. And maybe we have to say which compactification we start with, but for example, we can start with this one. Then this statement says that AG bar of 0, that's the first Voronoi. And then an interesting thing happens when you look at AG bar of 1. So if you look at, take k plus the boundary. And so Mumford and Hirzebruch. Mumford has an old paper called Hirzebruch proportionality principle, I think, and which says that this is the Satake. So this gives the contraction to the.
Do you know then, going back to the MG, what is the relative minima log minima model for MG equals 1 to the scale of 4?
So since it's an absolute canonical model, then it's also relative, right? K plus B is already ample, even absolutely. So the answer is the same. When this canonical model exists, it's just the same. But I'm saying even for G equals 3, you can go all the way if you do it relatively over Satake. But if you do it absolutely, then you cannot go to 0 certainly, because MG bar is M3 bar is.
You can finish this process.
Huh?
You can finish this process.
Right. So absolutely, it was finished. So there are papers of these authors that did it for G equals 3 completely. And so I think it kind of stops here. So, right, it's 1728 is the last number for G equals 3. Then for G equals 4, there is another jump. And for G equals 5, there is more. But MG bar is not of general type, right, for G equals 3. So it goes to the end, it goes to a point. So.
I mean, doesn't compactification correspond to alpha equals 2 there?
And that's what I was going to say here. So that if you do just things by analogy and look at this k plus twice the boundary, then that's ample, and that corresponds to the Satake compactification. So it seems that the two pictures are somewhat parallel. I said what I mean. So this formally doesn't make sense, because for a log canonical model, this coefficient has to be less or equal than 1. But if you just look at this formally, the statement is that k plus twice the boundary is ample, not ample, semi-ample, and gives the contraction to Satake. So it seems that there is the two pictures are parallel, and but with a shift by one. So there is this maybe corresponds to mg bar of 1, which is mg bar, and this corresponds to that. And what second Voronoi corresponds to is not clear. So let's so let me ask a more refined version of my question. Before I do that, let me introduce the standard toroidal compactifications of AG, and so that we know what we're talking about. So there are, first of all, toroidal compactifications of AG. So at first, when you try to enter this subject, it seems a little daunting, this task, because, well, there is a lot of theory and maybe hard to understand. But if you know some toric geometry, and you know a dictionary of how to translate from usual toric your knowledge of usual toric geometry to this situation, then it becomes very easy to understand. Maybe still not easy to prove, but easy to understand. So let me tell you this dictionary, so you can understand those toroidal compactifications. So in the toric geometry, there are two lattices. One is called M, the other is called N. So M is for monomials, so that is isomorphic to Z to the R. N is the dual lattice that corresponds to one parameter subgroups. So there are two dual lattices, and here you have the fans, and here you have polytopes. And fans describe arbitrary toric varieties. Polytopes describe projective toric varieties. And if you have a polytope, you can look at in the dual space, you can look at the normal fan. So that gives you a normal fan. So you can go from polytope to a fan. Now, in this theory of toroidal compactifications of AG, first you begin with the lattice lambda, which is Z to the G. And then you define these two lattices, N and M. And M is the second symmetric square of lambda. So it's isomorphic to Z to the power GG plus 1 over 2. And N is the dual of that lattice. And this is where this tau of the fan lives. And this is where the infinite polytopes live. And so when you have some sort of infinite polytope, that corresponds to a projective toroidal compactification. And an arbitrary toroidal compactification corresponds to a fan. Now, speaking in invariant, well, this is in the invariant way. If you want to talk in coordinates, then M is the space of matrices G by G matrices with coefficients in Q, which are symmetric, and are half integer. So AII are integers, and AIJ for I not equal to j are half integers. So they correspond to z-valued integral forms, quadratic forms, and the dual space is the space of symmetric integral matrices. And the pairing between n and m is so A dot B is the trace of AB. So that makes these two matrices into dual matrices. Now, if we look at over R, then we have the same two spaces here. And this is the positive definite quadratic form on that space. And there is a cone C. This is the cone of positive definite quadratic forms. And then there is C bar. This is the cone where we add semi-definite quadratic forms, but with integral coefficients or with the rational coefficients. And we take the closure of such matrices. Now, the fan here has to satisfy two conditions. First, the support of this fan has to be C bar. And secondly, modulo of the action, the natural action of GLGZ, there have to be only finitely many cones. So these are the conditions on the fan. And if you have such a fan, then there is a toroidal compactification of AG corresponding to it. And the three compactifications are the first Voronoi, the second Voronoi, and the Gusa blow-up. So let me introduce them. So here's how the first Voronoi is defined. You look at this C bar, this cone of semi-positive matrices, and you intersect it with M. So let me draw a picture. So there are. You look at all the integral matrices in this cone. And you look at the convex hull of that. So there will be some extremal integral matrices. And then you look at the cone over that. So that's a polyhedral figure. And that's the first Voronoi. That's how it's defined. Now, I mentioned this fact that, and I told you it's very easy to prove that this first Voronoi is the canonical model for any G over Satake. And so here's how it's proved. So if you recall your toric variety, then you know what Fano varieties correspond to. So if you have, in the space N, if you have a fan, there are rays. So then you take, on each ray, you look at the closest integral vector. And you connect them. If you get a, so this integral, the closest integral vectors, that corresponds to the divisor minus k. And so if you get a convex figure here, then that's the condition for minus k to be ample. And so a condition for this variety to be Fano. Now the condition for the canonical singularities is that there are no integral points inside of this polytope. So there is nothing between the boundary and this. Okay? So this is the usual toric picture. Now what this picture is, it's exactly the same picture but inverted. Just done, instead of convex this way, it's convex that way. So because these are the closest integral vectors on the rays. And so if it were convex this way, then minus k would be ample. And because it's convex the other way, then k is ample. And this picture, the usual toric variety, you should think of it as the absolute case. So these toric varieties live over a point. And this picture is for the relative case. So this picture is for the map to the Satake. So all the considerations here they're relative to this map. And so because it's convex, then k is ample. And because these are the closest integral points, there are no integral points before that. And so therefore it has canonical singularities. And so that's it. So that's why this first Voronoi is special from the birational point of view. That's why. Now the second Voronoi. Let me say something about the second Voronoi. Let me try to define it quickly. So here's the picture. So we start with this lattice, lambda, which is e to the g. And we start with some quadratic form. So this is a quadratic form. And so then for every vector v here, we add one more direction, which is r. And over this vector v, we take a point which has the coordinates v and q of v. Q is the quadratic form. And so we have infinitely many points here. And because the form is positive definite or semi-positive definite, it's kind of curved up. So then the definition is we take the convex hull of that, of this picture, and we get something polyhedral, and then we project the faces. And so the faces, when you project them down, there will be polytopes, or if the form is positive definite, or almost polytopes if it's semi-positive definite. And this picture will be periodic. And it's periodic because this is a quadratic function, and the first derivative of a quadratic function is linear. And linear function does not change this projection. If you add a linear function to this, then the projection will be the same. So the cones in the second Voronoi, so cones in the second Voronoi, they are in the bijection with such periodic ZG periodic tilings of RG. So this is an example of such a tiling. So that's what distinguishes this decomposition, that every cone has a geometric interpretation like this. And when you look at this tiling, you can interpret this as a variety as well. You can just look at this and you can see variety. For example, if you look at this, you see that this is a P1 cross P1. And this is another P1 cross P1, so there are lots of P1 cross P1s here, Z squared worth of them. But then, after you divide this picture by Z squared, there will be only one P1 cross P1, but it will be glued to itself. And so this side will identify with that side, and that side will glue to that side. And so you will get a projective variety. And so that will be one of these degenerate varieties on the boundary. So that's the geometric picture here. Now the Gusa blow up. Okay, let me skip that. Let me skip that definition. It's different from the. Okay, I'll say it in words. So in word, I'll just define it. So here's what you do. You look at C and you intersect it with M. So I recall this is where the monomials live. And so you look at the positive definite, strictly positive definite semi-integral matrices. And you look at the convex hull of that. And that is like an infinite polytope. And then you take the normal fan of that. And the normal fan is the Gusa blow-up. That's what it is. Now, this compactification is projective by definition because it comes from a convex picture. And this compactification is projective by definition. This one is projective for a non-trivial reason. So that's a theorem. So we have three projective compactifications here. They come. There are other names used for these compactifications. This first Voronoi otherwise is called perfect compactification. So first Voronoi cones are perfect cones. And the Gusa blow-up otherwise is called central. And here's how they're related. For G1, 2, 3, they're all the same. They all coincide. For G equals 4 and 5, the picture is as follows. There's this first Voronoi compactification, and it's the same as the Gusa. And by the way, it's called the Gusa blow-up because what it is just you look at the satake and you blow it up along the boundary. That's the blow-up. And then you normalize. And this is the fan you get. So for G equals 4 and 5, these two coincide. And the second Voronoi is maps to it. So the second Voronoi fan is a subdivision. And for G equals 6, okay, these two are different. And the first Voronoi, there is a claim. There's a there is a research announcement by Erdal and what's his name? Rybnikov. From 2001, where they announced that this fan is not a subdivision of that fan. So that, which means there is only a rational map, but not a map. And well, there is no proof; it's just an announcement. So that's the picture. So now we can formulate a more precise question, and the question would be this. So there is this second Valery, compactification, and over it there is this family of pairs. This is the geometric compactification. So the stack comes with a geometric family, with a flat family of nice projective stable pairs. And there is this first Valery, which is the canonical model. And for G up to 5, there is a morphism. And for G starting with 6, there is only a rational map. This rational map, so does not create divisors. Does not create divisors. That part is obvious. So it may blow up something, but it does not insert new divisors. So it's kind of small. So it looks like a flipping contraction. That's what it is. Or a composition of some divisorial contractions and flipping contractions. And so the question is, can we fill this? Can we fill this with a flat family here? That seems to be the natural question. So let me formulate give some answers. And my first theorem will be in the positive direction. And the second theorem will be in the negative direction. And so in the positive direction, the statement is that there exists a flat family of stable semi-Bilic pairs, varieties over this first Valery. So I can construct such a family. So I can, I can construct some geometric family, some flat family here. And it even corresponds to some geometry, which is geometric. So I'll discuss a little bit this. And the second statement is that for G starting with 4, there is no family satisfying the expected properties. Modular properties. And I'll explain that part as well. I will say what we expect and what. Yeah. So what exactly fails here? Okay, so first of all, this first Voronoi, the way I defined it, it did not have much geometry. It was, again, the definition was that this first Voronoi fan is the convex hull, so it's cones over the convex hull of n intersects C bar. So there is this cone of semi-negative, semi-definite positive matrices, and we just take the convex hull of them over them. But so what are these rays? That's the question. And there is a theorem of Barnes and Kohn. Answer an old paper answering a question of Mumford, which says that the extremal rays are rank 1 matrices. So they are of this form. M is some vector, and we look at the square integral matrices of rank 1. So the corresponding quadratic forms are just squares of a linear form. So that's all they are. So therefore, every cone here, so every cone in this first Voronoi compactification, it corresponds to some collection of linear forms. Now, if you have a linear form, then you can look at the corresponding, you can dice by the level by the levels of this form. And so when you have several of them, then you can dice several times. So you do get some periodic picture. Some of such periodic pictures appear for the second Voronoi. So this happens when you dice by this picture and you do not create new vertices. So all the vertices of the polytopes here are in the original lattice. And so when you add too many of linear forms, so this is the bad case. So when you dice and some fractional vertices appear, then this does not appear in the second Voronoi. But you can still look at you can still interpret this historically. And so you can still interpret this as a projective variety. And so that's exactly what I mean here. So that's this family. And so the caveat here is that these are not principally polarized. So over the second Voronoi, there is a family which is principally polarized, which extends the family of principally polarized abelian varieties. They all come with a line bundle, whose top degree is G factorial.
Does that reflect the fact that you don't get a map to MG? I would say AG.
Which map?
Not from MG to AG1 formula.
I'll discuss that next. So that will be my last subject, that extended Torelli map. And so I'll get there. But actually, for any stable curve, you get a dicing like this by linear forms, and it's nice. It's always nice. So this case never appears. So as far as the map from MG bar, this never appears. It's always a nice dicing. So it corresponds to a principally polarized case. Okay, so now what are the expected modular properties? So what fails here? So here's what I would expect. So there is AG. So now I will just look at the case 4 because this is where it already fails. So there is first, second Voronoi, and first Voronoi. And here we have a family. And here we're trying to put something. So what I would expect is two properties. And so they may be, the first may be slightly controversial. The second one really should not be. But the first, I would say that where the two compactifications agree, the families should agree. So where the common part, the common open part, where the two compactifications are equal, then I would expect that the family is still the same. And so this is slightly controversial. Maybe this can be relaxed. But this theorem fails if that's my assumption. And the second property is this. This is the decreasing property. And here's the property. So suppose we can fill this, and there is some family x prime here. And take a point here. It's a point here, so it corresponds to a pair. And that point maps to some point here, so there will be a variety x prime. So you think of this case in dimension 1, where we start with some stable curve, and here we get some cuspidal curve, or the curve with tech nodes. So what I would expect is that the number of irreducible components of x prime is less or equal than the number of irreducible components of x. That this map is from x to x prime. It doesn't have to be regular. It could be irrational. But the new irreducible components should not appear. Now about this expectation I feel strongly. So of course it's true in dimension 1. But also there is another example, a very large class of examples which I decided to skip for the lack of time. And that is compactifications of hyperplane arrangements. So if you start with the moduli, with the space of hyperplane arrangements in general position, there are many compactifications which correspond to weights. I constructed those. And so there is this whole set of spaces, and they're also ordered. So from a bigger one to a smaller, from a bigger modular compactification to a smaller modular compactification, there is a map. Between the universal families, there is only a rational map, but it has this decreasing property. So it may blow up a little bit, but it does not insert new reducible components. And so just looking at that example, I feel strongly that this should be the general property of higher dimensional case. And so with these two properties, this does not exist in this case. And the proof is just the analysis. So these are these are known explicitly in detail. And if I had more time, then I would draw pictures for you. I would say what they are and how a cone here is subdivided. but just looking at the family, at this family, so that is impossible. Now let me come to the end. I don't have much time, so let me talk about the extended Torelli. Extended Torelli map. So here's the picture. We have MG and we have AG. And then for MG, we look at this Dilling-Mumford, MG bar. And for AG, we look at one of these toroidal compactifications. And we ask whether there is an extension, an extended morphism. And so one can ask this question for all three of the standard decompositions. And historically, the Gusa blow-up was the first one to be considered. There is a paper from 1970s, whose title is on the extension of the Torelli map to the Gusa blow-up. And so this question is still open, as far as I know. This is not known. Now, for the second Voronoi, again, from 70s or 80s, the answer is yes. This map is extended. It can be extended, and so this is due to Mumford, and it's written up in a paper of Canonical. And so the proof. So the proof here. What is the proof? Let me say briefly. So. So MG bar is, of course, as a stack, is smooth, and so it corresponds to a cone. It's toroidal, so it corresponds to a collection of simplicial cones. And for every stable curve C, there is the graph, the dual graph of the stable curve, and from that stable curve you get a picture with the cone and some linear forms. So L of I of x, these are linear forms on the first homology of this graph. And then the corresponding quadratic forms are just the squares, these dices for those quadratic forms. And then the question is, as in toric geometry, you have a map of toric varieties if one fan maps inside of the other fan. And so here you start with this toroidal picture. You get a cone with these vectors, and the question is this cone inside some cone of the fan here? That's the combinatorial question. And for second Voronoi, the answer is yes. It's because, as I mentioned, these dicings are nice. No new vertices are created. That's the proof here of Mumford. And for third, so this is a claim, okay, I'm making. That the answer is also yes. So if I had time, maybe I would show you the proof. but okay, but it's also, maybe it's for the best. It's slightly tentative, so I would bet $100, but would not bet $1 million that my proof is correct. Okay, now, and I'm still not finished. So let me take two minutes, and then I'll be done. For the first Voronoi, I'm claiming, so that there is a quotes, yeah, slightly, but it seems that the proof is almost obvious, that it's very clear. But so I think that the map extends to the first Bernoulli.
Can I ask if it is possible to figure out the divisor? Like if you figured out the map, did you figure out the divisor?
Oh, the divisor, the pullback?
Yeah.
I have to think. I know why you're interested, but I have to think. Now let me say really quickly that see here we started with mg bar and we have all these mg alpha bar, right? We have this picture where alpha decreases, and wouldn't it be natural? Therefore, and so I'm saying that that this picture, this extends. That's what I just said, and all of this leaves over Satake, which is mg of 2, which maps to ag of 1. So all of this is relative to this map. So wouldn't it be natural if and if all of these maps also extended, if there was maybe just a shift by 1, and a picture here and a picture here, and all the Torelli map extended. And so when I mentioned this to Ian this spring, he said that he feels that this would be maybe too greedy to ask for it. And so after thinking about this, I have to agree that perhaps that is too much. And so I'll finish with the following very quick example.
How many spaces do you have in the lower row? You have much fewer spaces there.
That's right. So there is basically there are 2 which feel geometric. This first Voronoi, second Voronoi. So we can look at these curves which are cuspidal, and we can apply Torelli to it. The Torelli, the extended Torelli, you just send a curve to its compactified Jacobian. And you ask, where does that compactified Jacobian live? Does it live on the first Voronoi or on some other toroidal compactification? Is it naturally a point parameterized by some other toroidal compactification? That's the question, the natural question. So we know the top, the bottom we don't know, let's say. But we know the top and we know these arrows. We can compute compactified Jacobians. And so we can ask where do these arrows naturally go? And let me just finish with this example. And so this is with Dave Swinarski. So we discussed this with Dave, and we figured this out. And the example is very simple. It's for g equals 3, and it's the first thing. So what happens on the first step? And so the first step is that we have some curve of genus 2 with an elliptic tail. And in this first contraction, this curve is replaced by a cuspidal curve. All right, so what is the Jacobian? So the curve here is D, and E. So what is the Jacobian of this curve, C? Well, that's very easy. This is a curve of compact type. So it's just the Jacobian of this curve plus the Jacobian of this curve. Now, after we contract it and we got a cusp, what is the Jacobian? What is the compactified Jacobian of this curve? Well, let me tell you. It's just this cuspidal curve plus the Jacobian of D. That's what it is. That's what the compactified Jacobian is. And so what happens here, for curves, what we do on this in this first step, when we get cusps, we forget these elliptic curves. And what happens to the corresponding Jacobians is the same. We forget these summoned. this direct sum on the elliptic curve. And the conclusion is, but you see, this thing that we contract here. So we start with some compactification, for example, the first Voronoi. And where this naturally goes, what we contract, it's not on the boundary. It's inside. Because this was an abelian variety. This thing was in the interior of AG. It was not on the boundary. So when you look at this picture, this is not a compactification of AG. This some boundary, some interior of AG is contracted. Namely, abelian varieties which are of this form, which are direct summands of two abelian varieties of lower dimension. They get simplified, they get contracted. So if you're looking for the two parallel pictures here, these are not toroidal compactifications. These are compactifications of some open subset of AG. And so after all of this, after this investigation, I think my conclusion is still that the second Voronoi is the only geometric compactification of AG. So now I can say with some confidence because I looked into this. And I will stop here.
Are there any questions or comments?